Okay, now I'm in PowerPoint and it's going forward and you're hearing me.
Yes,
This is
fine.
still Hugh McLaughlin on the left. This is still Raj Pashari from the IPCC, and the person taking the picture is still 3 feet tall. One of the results of a pithy, clever title is it locks you into a couple different perspectives, and I'm going to go through them, but I don't want to be misrepresenting the scope of this particular discussion. It's really some perspective that I've gained from a decade or so on biochar, but additionally 40 years designing chemical reactions and processors. My doctorate was on chemical reaction engineering. We do a lot of esoteric things, but it allows me to look back over decades and give some advice. And hopefully, as they say, experience is a wonderful thing. It lets you recognize a mistake the second time you make it. I'll hopefully share some mistakes and you won't make them the second time. This is a slide of a book that has come out recently from this organization, and I urge people to access it. It is 2019 information and much more relevant than some of the things I'll be presenting. And I'm quoting from this book in chapter 1. Now, slides that have text on them, I don't like to read the text. I like to merely point out the highlight, the takeaway. I think the takeaway from this one is that slow pyrolysis is likely to be the foundation of scaling up biochar processors and industry applications, because frankly, it has some basic advantages when it comes to the properties of the biochar that hydrothermal carbonization and fast pyrolysis can't achieve. The takeaway on this slide is the fact that the current state of knowledge, temperatures between 500 and 600 degrees C are believed to be the most reliable choice. And that is to start steering you away from the lower temperature chars, which are previously been used as charcoals, which is a fuel and a chemical reductant for metal reduction. But we'll see that again. And within this particular book is a whole chapter on industrial technologies for slow pyrolysis. It's quite comprehensive. It is basically building on existing devices that are available in the marketplace. And this talk is going to try to look more at some core fundamental phenomena that should be incorporated into a biochar processor designs, which is looking forward to the design as opposed to looking back on its advantages and disadvantages. So we're going to look at constraints, and everyone likes Wikipedia. So a constraint is a limitation or a restriction. The biggest constraint is we are working with lignocellulosic materials, plants, and they consist of, as depicted here, hemicellulose, lignin, and cellulose. There are resin components and some other minor components, but the majority is cellulose and hemicellulose and lignin. The colors are subject to discussion, but the structures are fairly representative in conceptual ways of the complexity of the mixture we start off with. The second constraint is we need to be a bit faster than the traditional practices as applied to coal. In other words, we have to be basically 1 minute for each million years of evolution of these materials. And finally, and we'll see this again, when we look at making thermochemical transformation of biomass, we have the ability to go from about 300 to maybe 900 degrees Celsius. And within that range, you make two different materials. One is the very bottom end. At 300 degrees C, the material is soundly black. It's a char at that point, and it's the best fuel you'll make because it has a lot of volatiles, it burns nicely, and the yield is quite high. If you continue on to higher temperatures, the yield drops off, you have less product to sell, you are transferring more energy to the vapor stream, which could be condensed and burned off, but Bottom line, your yield is lower, so you have less solid product, but you have picked up a new property, which is absorption. This is the activated carbon analog. Biochar is Mother Nature's activated carbon. So we need to remember when we're making a biochar that we can't just relabel the bag of charcoal biochar and sell it to the unsuspecting consumer. So now let's look at some considerations. Actually, the first 3 slides were just the constraints. You have to live within that. Now let's give some careful thought, typically over a period of time, to the fact that as we are heating these materials up from room temperature, 100 degrees C, where they start to dry out, through to 300 degrees C, which, as you remember from, frankly, the previous slide or 2 slides back, is where these things become charcoal. They're not yet biochar, but within that window, we see this dramatic set of transformations for each of the major components. So they are, there's only one that exhibits a B, which is a glass transition temperature, which is a polymer phenomena where the thing becomes plastic and starts pseudo-flowing. But they go from drying to depolymerization to carbonization, and then they completely rearrange. And by the time you get to E, you have made a brand new material. They are atoms provided by the plant, put in locations as the plant grew, but the pyrolysis process is going to reconfigure. It's going to remove a fair number of those atoms, 75% of the weight, and it's going to leave the ones behind, which are much more carbon biased, in a new structure. So here is graphically, not graphically, there is visually the transformation over that duration at dried pellets, and then 200, 225, 250, 275, and 300 degrees C. And what you see is the torrefaction range in there. So the material browns, and then ultimately at 300, there's enough of the condensed aromatics to then have a black color. And from there on, it is almost impossible to tell anything about biochar by looking at it, because it's black and it doesn't really look a whole lot different than so a 300 degrees C char versus a 700 degrees C char look alarmingly alike. So we need to do more than just look at it and declare, yes, it's the right color, therefore it must be biochar. So what is happening as we go through this range and all the way up to 700, 900 degrees C is we are subjecting the solids to thermal conditions that they have never seen before in the course of the material's life and its evolution. And therefore, we start losing, devolatilizing, losing smaller molecules, some carbon, but predominantly the oxygens and the hydrogens form volatiles and they escape and they're gone. And what's left behind is the carbon atoms, which then link up to start forming these 5, 6, and 7 membered rings. And what's not shown on this particular slide is what's in between these. These are not all hovering in ether. What is not shown is the tars. So we have other materials that haven't yet formed the aromatic clusters or haven't integrated into an aromatic cluster, a graphene sheet, so to speak. But they are there and they are heating as these are and continuing to consolidate. And what you end up with is this, which is a highly interwoven, locally non-ordered, non-crystalline material. Each of the colors is representing kind of a discrete graphene sheet, and it is a very porous material. And it is a backbone of about 1.5 specific gravity and a density of about 1/10 of that. So it is a lot of open space, a lot of vapor. One of the other considerations we have is all the work that's been done. Charcoal is essentially the first man-made modified chemical material. Take wood, char it, you make charcoal. Charcoal's advantage is it burns with much less smoke, so you can burn it inside the cave and cook over it. So there's some great work that's been done. I refer everyone to Antel and Groli's work of 2003. It is, however, charcoal centric. So he's viewing this material as a fuel. He is not looking to any great extent to the unique qualities of biochar, which is things like the microporosity and the edge chain functionalities that play an important role. He does give some lip service to renewable fuel, reductant, absorbent, and soil amendment, but this is pre-biochar days, and so there's really nothing other than trying to become more important than the scope of this particular article. However, this article is brilliant, and I urge everyone to access it. Within there is one of the data points, one of the temperatures that we convert wood to. This is actually higher than charcoal, lower than a good biochar. But the important concept is it makes it trifurcates the biomass into three streams. A solid, the carbonized residue, biocarbon, 35% of the weight at this temperature, 57% of the carbon atoms, over half in that subset. And then there are volatiles, of which we include the water, and then you have tars. So these are, this is an interesting split. The volatiles and the tars leave as vapors and then can be recovered. Although the tars may not leave entirely, as we'll see. So in Antel's work, there's a tremendous amount of data that you don't have to reinvent, but you should respect. The people that come out and tell me that they've got a new biochar process and the yield is 75% solids, need to respect the fact that we know they're lying or they're just bad scientists based on that claim, or they're selling us a bag of grit. So get to this data. These are very important trends. They're going to occur in your work. They're going to occur in your pyrolyzer design. Here's an example of where the carbon concentrations and the oxygens and the hydrogens. So it gives you an idea of what kind of temperatures you'd have to get to get to these. If you believe in H to C organic ratios as a goal, then you need to get yourself to 400 to 500 plus to even think about being in that, because these are mass fractions, weight. These are not mole fractions, and H over C organic is a mole ratio. And in addition, there's a paper out there which I am sure absolutely no one has ever read, and that's because it was given in a perfectly cushy conference in Banff, Canada in 2009. And I was with a company that was looking at using biomass to make biocoal. And so we looked at blending the material in with coal, and we did a lot of a thermal analysis. And in there, you'll find some smoothed out data, which is probably not quantitatively accurate, but it is qualitatively representative. And this shows you the trends of the carbons and the hydrogens and the fixed carbon yield, which is relatively low for biochar. I mean, again, you'd have to get the paper, but again, this data's out there, use it. This is a very interesting plot in that it allows you, it's a little bit complicated in the sense that the x-axis is split. So you're taking, we use 200 degrees C bone dry wood as our reference sort of pivot point. Materials to the left of that are increased moisture concentration. So as the moisture is removed, the energy density increases, the yield increases because I've taken away an endothermic obligation of boiling the water off, and the weight I have decreases. So that's the left-hand side for those three curves, and then they carry over and show you where you're headed. As you enter carbonization temperatures, they stop at 500 because things become less interesting. But again, these are important guides for you to think about when you're starting to put together a processor design that's going to be moving materials in and taking materials out. So don't reinvent these wheels. Get the data, use it, and then if you need to refine it or modify it, you can. In a real world process, This is an ideal sort of first law analysis. In a real-world process, there are some significant inefficiencies. So this is pelletizing. This isn't doing anything other than taking sawdust and putting it into pellets. And you see here that you have 15% of your input materials used just for energy to dry. And another 144 kilowatt hours, which is about a half a gigajoule per ton, is required as electricity, which is almost impossible to make from biomass on an economic scale, you know, if you're off the grid. So this is tied in, and this is the more real world kind of economics that you're going to encounter in a processor operation and one that's trying to make money in the marketplace. Back to one of the curves that was in that previous slide, which was the split one with the moisture and then the temperatures. It's interesting because you can very quickly see that if you're torrefying, you don't need to start with anything that's got more moisture than 30% because your torrefaction won't give you back enough energy to keep it going. So you're either going to have a separate energy stream, which we saw in drying for the pellets, 15% for drying the material, or you're going to have to supplement it with natural gas or some other energy source that we're not allowed to use anymore. But it also points out that at 350, we now are isoenergetic with 50% moisture, which is about as bad as biomass gets. A fresh cut tree is about half water and half biomass. And then beyond 350C, which is really just getting into the biochar region, actually you're not there yet, you're just leaving the charcoal region, you have lots of excess energy. And that's one phenomena of any properly designed biochar producing process is a lot of energy is coming off in that vapor stream as tars and non-condensables. They need to be dealt with. They could either become additional products, but they have to be properly oxidized if they're going to be discharged because they represent an enormous source of VOCs and atmospheric pollution. Going back to our favorite peak, we see a new curve, which is the red line, and that's the energy content. So the biochar and charcoal itself are much more energy dense than the wood they started from. And so on a weight basis, they have a higher energy per pound or per unit of mass. And we see that although we lose 75% of the weight, we actually retain just under 50% of the total energy that came in with all the incoming biomass. So there is an improvement, which is significant and is also something that results in charcoal being used as a fuel. We have an old saying years ago that it shrinks to about half the volume. Its density is about a quarter, or excuse me, its weight is a quarter, its volume is a half, therefore the density goes to about half that of the biomass. De facto, we were wondering somebody must be thinking, why does the peak go up and down? What's with the sort of mountain that says 600 is the optimum and then after that things fall apart? Some work was done years ago in which we looked at the density, the skeletal density, and what we find at the 600-degree mark is that the skeletal density of the graphite in the biochar is increasing from 1.5 to 1 to 2.0. Pure graphite would be 2.25. And so what is in fact happening, as has been sort of suspected, is the graphene sheets are starting to collapse onto each other, making a denser structure with less surface area available, not surface area, pore volumes available, but surface area is a reasonable analog for absorption. So it falls off. So you destroy a property you want to maintain. You can kill biochar. I wanted to show you that contraction, that loss of volume. This is an angle to show you the materials, but looking down on them, you can see that as you go up in temperature, there's incremental consolidation of the graphene sheets. And so it doesn't shrink to half the volume. It shrinks continually as it keeps going up. and the actual weight loss is relatively minor after about 500 degrees C, although that's hard to tell looking at it from this angle. So again, these are physical properties. The number of people over the years have said, you know, I put in wood and then I run through my heated screw and it comes out and it's only half full. You go, well, yeah, that's because this stuff condensed. It consolidated chemically at the molecular level and in the real world. So you're seeing, what you're seeing is what's really supposed to be happening. So you might as well plan on it. Again, build on known knowledge. This is one that we really need to focus on, which is the fact that in biochar and in charcoal, there are two kinds of carbon graphite being deposited or created. One is created purely out of thermal consolidation. The material never goes through a plastic or a liquid phase. And the second is one which is the tars and the vapors condense onto an existing charcoal surface, because charcoal, when it's formed, or graphite surfaces when they're formed, absorb immediately anything that's around them. And one of the things they can absorb is the tars. And those tars then cook and decompose. So what we find, and this is a very key aspect of a pyrolyzer design, is sweep, is what I call it. In other words, to what extent are you pickling the charcoal or the char in its own juices versus having some kind of a vapor flow that moves those materials out, gets the vapors that can recondense on the char out. And the reason that is important is that secondary char has very little absorption. It actually takes away absorption because it tends to absorb onto primary char absorption sites and then coke out or turn into additional char and cover those surfaces and remove those volumes. This is from Antel. He's really into high pressure stuff. At high pressures, you make higher char yields. That's because you actually intentionally condense these vapors into the charcoal. So any process or design, we need to look at it and ask ourselves, to what extent are these vapors that are being thrown off at various temperatures, to what extent are they likely to be reconsolidating into the char, and frankly, while increasing the yield, deteriorating the actual absorption property we may be wanting, because it has some unique features that really distinguish biochar from just shredded tires and biochar from activated carbons. So we have from Antel some quotes. Charcoal is black. Yes, we got through that earlier. It's, you know, got some physical properties you can measure. And in addition, it has, and this may come as a surprise, it certainly comes to a surprise to the processor designer, the reactor designer, when it happens, which is there are exotherms. You know, you're heating something up. Generally, they're endothermic. They're taking in heat, energy to move them up the temperature scale based on heat capacity. But there are a couple of periods where really without any additional outside vapor, this isn't combustion, this isn't due to oxygen, it's due to the tars getting to a point where they are too hot to be tars anymore, but they're too heavy to volatilize, and what they do is they disproportionate into graphene sheets. So graphite forms out of some of the carbon atoms, and then a small portion of them is given off as volatiles, but the net heat release of forming all those aromatic rings is so significant that there is these notable exotherms. So that brings us to my first concern. And concerns from Wikipedia is an uneasy state of blended interest, uncertainty, and apprehension. And frankly, that's a great description for a concern. Because from Antel's thing, we note that these exotherms represent somewhere in the neighborhood of 6 to 10% of the heat content of the feed. So by heat content, they mean the total amount of heat that would be released if you burned it in oxygen or air and made heat out of it. That's how we would measure it. hence the name heat content. So for a ton of wood, it has 15 to 18 gigajoules. So 10% of that is, you know, something in the 1.5 to 1.8, 10% would be 1.8 gigajoules. So my concern is this: you're pumping this biomass into your processor, and somewhere between here and the exit, it's going to kick back out at you 6 to 10% of its heat content. And is your pyrolyzer even designed to have that occur? And there are certain geometry. I mean, this is actually what causes retorts to take off, is this exotherm that suddenly bumps the temperatures up so much higher throughout the mass. And it also is what causes sealed retorts to blow up. But again, this is the concern. People go in and put these mechanical devices together, and they're not aware of the fact that halfway through you're heating it, and it turns around and decides to heat back and push you very rapidly to a new temperature regime. So that's a big concern. The other concerns are a little more academic. These are methods used by chemical reaction engineers, or methods used by the graduate advisor of chemical reaction engineer graduate students to torture them, but the basic use is to try to figure out what's going on inside. So there's a couple of ways of thinking about processors and the flows of material through them. One is called residence time analysis, or residence time. In other words, to what extent is everybody moving through what is the distribution of times that materials spend in there? And if that distribution is broad, that is going to result in a broad distribution of properties in the biochars. Similarly, there's an analysis called thermal time analysis, which is basically the residence time weighted times the kinetics of the temperature they're at, to see how much thermal time we occur. So it could be that if, because of reaction rates, 10 seconds at 600 degrees C equals 2 hours at 250 degrees C, or even worse. So it's useful to look at the processor and decide to what extent am I going to have significant thermal gradients within it, because these are going to be things that you would like to minimize in an effort to make a fairly uniform biochar product. At the end of the day, I have to say the biggest concern I have is that biochar is not an easy product to make, especially to make exactly the way you want to make it. Excuse me. Sorry. Some of the challenges are the material properties. It's a poor thermal conductor, yet it has a relatively high heat capacity if it comes in wet, the biomass. The conversion is entirely dictated by the temperatures, or dominated by the temperatures that are reached. But those things have exotherms that can move local temperatures in lots of different directions and can create oscillations in continuous processes that are trying to make us the same product, but because the incoming product has variability, the outgoing product has the same amount, if not more. And then at the end of the day, my biggest concern is that biochar is a highly variable material representing a wide range of properties, yet the impact of those variations on performance of biochar and the range of applications practiced or anticipated is essentially unknown. So that makes it very difficult to decide what you want to make, because you don't know whether you want to leave tars in or take them all out, or if you want to do modifications like the previous talk. So it's, I tell people making good biochar is really no harder than making good wine. Start with good grapes, don't make any mistakes, be lucky, and every couple of years you'll get exactly what you want. Biochar is actually easier than that. So the consequences. We're getting to the end. The result or effect of an action or condition. The consequence of pyrolyzing biomass to biochar is to create a material that is really so far beyond a fuel the charcoal. You would have stopped earlier, used it as charcoal, moved on. But no, we are making a material that has new properties and is entirely formed with new structures that we can control to an extent. By the pyrolyzer conditions and design, we can control it also to an extent by the choice of raw materials. And it's very, very flexible, so it gives us a tremendous amount of latitude. So we really have a fairly straightforward challenge. Heat it up, don't blow it up, and you're going to make something brand new that you can do things with. But you have to learn how to control that. And that's the challenge of designing pyrolyzers and testing them and then figuring out how to run them. Again, text here captures carbon atoms from the sky. It's a genuine carbon dioxide reduction mechanism for atmospheric CO2. It's terrific soil amendment. It has some additional applications we're just learning about as essentially mechanical materials in plastics and in concrete. And at the end of the day, biochar is here to stay, providing a set of applications beyond those of charcoal. You know, Adam made charcoal so Eve would cook dinner, and we're still using charcoal to cook dinner in a lot of places. We can do more by making biochar. And then this, it's really a beautiful material. Every once in a while, when you make biochar and you open up the retort, you'll look in and you'll encounter these kinds of colors. And what these are singlet electrons that as it consolidated, an aromatic ring came up one short. And there's an electron stuck in the middle, and that gives it the color property. It's a fascinating thing. It typically goes away in a couple hours, which is why you take a picture. And that's my talk. I will entertain questions, and thank you very much for your attention.
Thank you very much, Hugh. Again, really nice presentation. Déjà vu.
All right, I'm back to you, and I'm not screen sharing anymore.
Yes, and you already got your first question. Where is it?
I'll let you filter those.
Yes, so is there a pyrolyzer design that you favor?
Well, I have a company that has developed a technology, and if the patents issue, I'll be happy to tell you exactly how it works. Most of the designs that are out there, to be honest, are repurposed charcoal makers. And so there isn't enough to choose from. I only know of 2, maybe 3 commercial designs that I would say were put together after biochar became the predominant goal of these. I will note, that any design that has mechanical mixing available for the biomass is a tremendous improvement because it blends the materials and starts cutting down on these gradients of residence time and thermal time. You know, biochar reactors are, notorious for putting the material in and cooking it and taking it out. So anything that can mix is a plus.
And that brings us directly to the next question. So what do you think about microwave pyrolysis?
Total waste of time. As soon as you do the energy balance, you're going to realize that, this is kind of like the hydrogen economy. You start with a cup of water, you turn it into hydrogen somehow, and then you use all that hydrogen energy. Well, unfortunately, microwave is a more selective way of putting any energy in, but de facto, and I haven't done a lot of research on microwave biochars. I have tested a couple that I've seen. They aren't flawed, but I think the microwave is an energy intensive way of getting thermal energy into certain bonds. And there doesn't appear to be the huge selectivity we would need. Like it only heats up oxygen carbon bonds and cleaves them off, selectively, and therefore drives the condensates, the vapors, to being much higher in water content than we see with typical pyrolysis temperatures. So you don't have a huge advantage, you have an expensive energy stream, and it doesn't scale very well. I have, however, used them to dry biochar samples quickly in the lab. So that's a good one. But don't leave them in there for too long because they'll burst into flames, which some people view as a drawback or a distraction.
What does pyrolyzer design look like if you optimize it for heat production and treat biochar as a secondary product?
Well, that comes down to, is the energy, are you getting paid enough for the heat to intentionally gasify some of the char? Because you can always do that to any arbitrary extent. You know, if you wanted optimized heat, burn it to ash and you'll get all the BTUs coming off. It really comes down to where you're going to release that heat, because the big problem with pyroligneous vapors is they're not condensable. They have too much water vapor in them, so you can't compress them up and put them in a pipeline and take them, you know, across the plant or across the world. So you've got to turn around and at relatively low pressures move these vapor streams over and combust them to get the heat production. And these gases are somewhere between 150 to 250 BTUs per standard cubic foot. I apologize for the English units, but somebody out there that's younger than me will translate that into the right units. It's somewhere between a quarter to a sixth of the energy density of high quality natural gas or methane. So it's not a great fuel. You know, but if you're going to buy it off of me for $10 a gigajoule, I'll be happy to turn, you know, it all into gas.
You talked about mechanical mixing as an advantage, and Brian is asking, is a tumbling retort on the right track to achieve that?
Tumbling is on the right track. The problem, well, if you can get it to be a retort, that's the right track. The thing you're missing in retorts is sweep. So you get to a point where you say, can I tumble it? Could I take some recycled flue gas back through and sweep the tars away from my char as it's forming to prevent that secondary charcoal formation? These are all steps in the right direction, but the mechanical complexity can at times drive you crazy. But again, my goal on this talk here was to try to flag things that you can refer to when you're making your mistakes on paper, as opposed to assembling a pile of steel and finding out that it makes essentially glorified charcoal.
So just a quick question for myself. So what would you say is a good size of a pyrolyzer to achieve things like mechanical mixing, sweep gas? What's a useful minimum size? What would you say?
Well, I think the minimum size, you have a huge economics of scale. So the bigger the better for the marketplace, because biochar is going to be a commodity that's going to sell. And while you may make the world's greatest biochar, I doubt you're going to command 5 times the price per unit of weight than a relatively middle of the stream biochar. So, you know, there isn't a scale beyond the mechanical limitations. These devices are not terribly demanding, correctly designed, on materials. You don't need ceramics, you don't need high temperature alloys, etc. 304 is recommended, but it's not necessary if you keep things dry. So it's really, you know, the balancing of the conditions that I think is to be struck. And it's hard to give a quantitative answer on essentially. So bigger than small and smaller than huge.
One question from Felipe. How much longer do you think we will need so that we develop the required standards and regulations for safe biochar use?
Well, I think we have currently the required standards for safety. And frankly, there's very little issue if you start with clean biomass. It doesn't have heavy metals and doesn't have man-made toxicity like Agent Orange. the biochar process, carbonization, does not create these draconian molecules that the world would have us fear. You know, forest fires don't leave desolate landscapes behind. So the IBI standards and EBC standards are quite good at eliminating, guaranteeing safety. What they are completely worthless for, as my last seminar attempted to convince people, is to quantify quality and measure above just being safe. So they're two different objectives. And I don't think that biochar with clean raw materials, if you know where you're starting, you should not be, you know, thinking that you're going to create something. Because frankly, if the biochar has any absorbency at all, which it should to be good biochar, it's going to keep all the toxicity.
And I think one of the last questions from Kim, what do you think about hydropyrolysis? So I think hydrothermal carbonization.
Right. I think it is a graduate student's dream because it's relatively unstudied. It can be done in a PAR reactor, in the bench, etc. But as you start scaling these pressurized processes up, they become nightmares. Frankly, you make a very different material. You don't make a biochar. You make essentially a hydropyrolysis coal, or coal substitute, which may emerge as having completely different properties that are advantageous, but they are not a reasonable alternative to making slow pyrolysis biochars that are used as absorbents or used as soil amendments. But the grant writers seem to think it's like the next panacea. It's like BioOil. BioOil is every graduate student's dream and every researcher, because it never hopelessly fails. But it also has more research that needs to be done. I mean, you could spend millennia working on BioOil. Hell, you ought to spend some time renaming it. It's not an oil. It used to have a different name that was more representative. It was called tar. And I really think tar covers it a little better than BioOil. And BioOil sounds like something you rub on your legs when you're in the sun. Anyways, my political orientations seep through.
And I think the last question from Gary now, or second last question. Do you think there will be any new industrial technology in the upcoming decades? Alternatives to current technologies like kilns, retorts, etc.?
Yeah, the answer is absolutely. We are now seeing people not repurposing, but rather thinking about how they could make biochar and capture the various streams and fractionate them and turn value products from them. So we're seeing it now. Yes, the days of saying, we've been making this for 200 years, it was called a lime calciner, but we found out yesterday that we could stencil biochar maker on the side of it and sell it for twice as much. Those days are behind us.
And now, nice question for the end. So what's your personal opinion on where we will see the commercial mass market adoption of biochar products? Agriculture, fertilizer, concrete, or others?
I'll tell you, the thing about biochar is all the applications are essentially infinite in market scope. So the day biochar, the day a pound of biochar or dollars worth of biochar is a better investment for the farmer than a dollar's worth of fertilizer or Roundup, is the day that biochar demand goes to infinity. I think the places that'll first get traction are high valued commodity crops like tomatoes and row crops and things like that, because of the better yields. And needless to say, marijuana is the one that's jumped all over that, because it really does help grow marijuana under very difficult conditions, because it's regulated and they make them grow it indoors. So it's coming along. I think it's going to find a complete diversity of applications. because frankly, it is a completely new material. You can make, I mean, it astonishes me. For 20 bucks, I can build a 1G 2-can T-Lud and take wood pellets and a fan, and I can make a material that has half the absorption capacity of a full-blown coconut shell activated carbon on a weight basis. So for 50 bucks, I'm making quantities of activated carbon like decontamination, and that can be distributed throughout the developing world that has all the pesticides and waters and all that other stuff. So the potentials are limitless, but the markets are not well defined. And that's the challenge. We have, we have standards to prevent toxicity. We don't have characterizations that allow superiority of a product to be recognized and sought after.
Okay, but now really the last question from Mari Selvam is, because I think you are quite well suited to answer that. How close do you think modeling studies for the design of pyrolyzers are correlated with real performance of the reactors?
Well, only a third of the PhDs in the world have the word modeling in their title. So frankly, modeling is an art form. I think modeling can come as close to the real performance of the reactor once you build the reactor, run it, and then go back and tweak the model to then become a predictive tool. It's not, there's nothing conceptually preventing you from being dead on, other than there isn't a large enough computer and you don't have enough data to fit the model. But the models are pretty robust, or you can, create analog models that get close enough to the properties you need. So I don't think it's an intellectual challenge, it's an academic priority. There's very little money being thrown at modeling or building pyrolyzers in academia. And those are the people that generally take on these challenges. We'll get there. Just throw $1 billion at it. It'll happen tomorrow.
I think that's a nice closing sentence.